In science, there's a pretty crazy idea that a flap of a butterfly's wings could eventually cause a storm on the other side of the world. Sounds completely insane, right? I mean, how could this tiny little butterfly possibly create something as massive as a storm? But guys, as weird as it sounds, that's actually how the world works. And that idea is known as the butterfly effect. In this video, we're going to talk about that idea. The idea that even the smallest changes can eventually lead to massive consequences. So get your brain ready, because some of the ideas we'll talk about might genuinely blow your mind. Let's talk about it. Back in 2004, there was a pretty wild movie called The Butterfly Effect. If you haven't seen it yet, honestly, I'd recommend checking it out. The movie tells the story of a guy named Evan who suddenly discovers that he can travel back into his own past whenever he reads his old journals. And with that ability, Evan starts trying to change the terrible things that happened to him and his friends years ago. But guess what happened? His future stays messed up anyway. Because every time he manages to prevent one tragedy, another one shows up to take its place. And the more often Evan goes back to fix his life, the more he starts realizing something terrifying. Changing the past doesn't automatically mean he can predict or control the future. Because no matter how small the change is, it can eventually set off a chain of events that completely changes the future. Now obviously, traveling back in time is just movie fiction. But what's interesting is that a lot of the ideas behind this film were actually inspired by a real phenomenon in science. A phenomenon that has confused scientists for centuries. And to understand that phenomenon, we need to go back a few hundred years. You probably know, or at least have heard, names like Zeus, Poseidon, Hera, and many others, right? Yup, the gods of ancient Greece. Back then, people believed in these gods because they couldn't explain the things happening around them. Phenomena like lightning, earthquakes, volcanic eruptions, and countless other natural events were believed to be the work of the gods. Doesn't make sense? Of course it doesn't. And that's exactly why centuries later, names like Galileo, Kepler, Copernicus, and many other scientists started to show up. Because at that time, people started questioning those beliefs. They began separating mystical explanations from rational thinking. Instead of blaming the gods for everything they couldn't understand, people started looking for answers through observation and mathematics. This movement eventually reached its peak in the 17th century, when Isaac Newton published this book. In this book, Newton introduced two laws that would completely change the way we see the world: the laws of motion and the law of gravity. Through these laws, Newton showed that objects in the universe actually move according to incredibly precise mathematical rules. From an apple falling from a tree to the planets orbiting the sun, all of it could be described through mathematical equations. And these laws didn't just explain what was happening, they could also be used to predict what would happen next. In other words, they could be used to predict the future. Even at that time, Pierre-Simon Laplace, a great mathematician from France, came up with something absolutely crazy. He said, if there were an intelligence capable of knowing the exact position and velocity of every particle in the universe, that intelligence wouldn't just know what's happening right now, it would also be able to see the future, and even the past. In other words, according to Laplace, the future isn't really a mystery, it's just a math problem. Laplace even suggested that God wasn't needed to explain the order of the universe.
So, Laplace developed perturbation theory. Do you know who summoned up these books to read them immediately? Napoleon. He reads it, goes to Laplace and says, this is a beautiful piece of work, brilliant, but you make no mention of the architect of the system. He's referring to God. And Laplace replied, sir, I had no need for that hypothesis.
Ooh, that's a mic drop. Ooh, that is tough.
But that belief eventually came crashing down a century later, when another great mathematician from France, Henri Poincaré, introduced a concept known as chaos. But hold on, it's important to understand that chaos in this context doesn't mean disorder. Chaos in this context is a system that still follows the laws of physics, a system that's incredibly orderly. so orderly that its final outcome becomes impossible to predict. Okay, I know that probably sounds confusing, but before you click off this video because your brain is starting to explode, take a look at this animation first. As you can see, there are two balls here. One is green and the other is brown. The green ball seems to move in a very predictable way, right? Meanwhile, the brown ball appears to move completely at random. That's because the green ball is attached to a simple pendulum. But take a closer look. The brown ball is actually attached to a pendulum too. The only difference is that this pendulum has two arms. And this is what's known as a double pendulum. No one and no method on Earth that can accurately predict the path of a double pendulum over long periods of time, not even with a computer.
You'll see the sort of very irregular, hopefully you'll see the very irregular kind of way in which the lower pendulum oscillates around. And it would be very hard to predict, for example, with a computer, how that lower pendulum, will it go around once? Well, yes, just made it.
And it's practically impossible to make a double pendulum follow the exact same path twice, because even the tiniest difference in its starting position will eventually grow larger and larger until it produces a completely different trajectory. Another example is this magnetic pendulum. No matter how many times you try to swing it from the exact same position, it will never follow the exact same path twice. Why does that happen? Well, because the truth is, we can never place this pendulum in the exact same starting position. There will always be a tiny difference. And even if that difference is only a fraction of a millimeter, the path it takes can end up being completely different. And this is what we call chaos. And that's exactly what Henri Poincaré was talking about. The future isn't as simple as a math problem, not because the equations don't work, but because we can never know the starting conditions of a system with 100% accuracy. And almost everything around us, or maybe even everything around us, seems to have this kind of chaotic behavior. And one of the best real-world examples of chaos is the weather. Alright, now I want to introduce you to this guy. His name is Edward Lorenz. He was a meteorologist from the Massachusetts Institute of Technology, or MIT. Back in the 1960s, Lorenz and his team set out to do something that had never really been done before. They wanted to predict the weather using mathematics and computers. The idea was simple. If the weather truly follows the laws of physics, then a computer should be able to calculate how it will change in the future. So Lorenz created a computer program designed to simulate the weather using different variables, such as temperature, air pressure, humidity, and many others. The first simulation ran perfectly fine, so Lorenz decided to run a second one. For the second simulation, he simply used the results from the first one as the starting point. He entered the data, and then he stepped away from his computer for a while, maybe to take a nap, I don't know. But when he came back, he found something that completely shocked him. The graph from the second simulation had drifted far away from what he expected. At first, Lorenz thought there was something wrong with the computer, but after checking everything over and over again, he realized the computer wasn't the problem. The problem was much smaller than that. Lorenz entered his simulation data using only 3 decimal places, even though the program was actually using 6 decimal places. Now, if you're familiar with math, the difference between 3 decimal places and 6 decimal places is incredibly small, only a few thousandths. And in most cases, a difference that small wouldn't even matter. And remember, Lorenz was trying to simulate the future weather. And with that tiny difference, the final result deviated significantly. From this, we know that it's impossible to accurately predict the future, because we'll never be able to obtain that data with 100% precision.
And I was rather dismayed at first when I came back an hour later after 2 months of simulated weather and found that it wasn't behaving the same way because we'd had a lot of trouble with our little computer, and I thought this was more computer trouble at first. And then when I looked at it more closely, I realized that what was happening was that I hadn't put the same numbers in. I'd put in rounded off versions of the numbers, and these small differences had amplified, doubling every few days until they became so large that they drowned out the signal.
This discovery eventually led Lorenz to write a paper that became known as the butterfly effect. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Of course, the butterfly was just a metaphor. What he was trying to say was, Can something small, even something as tiny as the flap of a butterfly's wings, eventually lead to something as massive as a tornado? And because of Lorenz's paper, the term butterfly effect started showing up everywhere. It's used to describe situations where a system ends up behaving completely differently because of a tiny change that should have been ignored.
When I was a graduate student, the belief was, as we got more and more computer power, we'd be able to solve ever more complicated sets of equations. But this said that's not necessarily true. You could have the simplest equations you can think of, with nothing random in them. You know everything. And yet, if they have behavior that gives you chaotic solutions, then you can never know the starting point accurately enough.
But the point of the butterfly effect isn't about the butterfly or the tornado. It's about how this theory changes the way we think about the future. Because if something incredibly small can lead to massive consequences, then who can say that the small things we do today won't change our lives tomorrow? Maybe right now you think watching this video won't make any difference. Maybe right now you think spending 15 minutes listening to a theory about chaos is just a waste of time. But who knows? Maybe one small idea you hear today will make you see the world differently. Maybe it'll make you curious enough to learn something new. Maybe it'll lead you to make a different decision a few years from now. And maybe that decision will eventually take you to a future you never imagined. Isn't it the fact that the future is mysterious and unpredictable that makes us keep trying our best every day?